This is Physics 1020 and 1090 for lecture for Friday, April 17th. This is video 2. We're going to discuss Practice Exam 4B, and this is going to be the last video I record for the entire semester. So we're going to discuss Practice Exam 4B. Hey, remember, the questions may be in a different order when you took the exam, but we'll go through them one by one in the order that I saw them. There's a question on Compton scattering, and it said that you send in an X-ray with a wavelength 0.0034 nanometers, and it hits a stationary electron, and then the electron recoils one direction, and you have a scattered photon, a scattered X-ray in another direction, 75 degrees, and the question is, what is the scattered wavelength? Okay, first of all, let's calculate the shift in wavelength. That's the Compton formula. The shift in wavelength is Planck's constant over the mass times speed of light times 1 minus cosine theta. So I put in Planck's constant, the mass of the electron, and speed of light. Remember, you can find these quickly in the appendix of your book. And then 1 minus cosine 75 degrees, and you do the calculation, you get 1.8 times 10 to the minus 12 meters. And we'll always be converting things, often, usually, to nanometers. So that's 0.0018 nanometers. Now that's the shift in the wavelength. The question asks for the wavelength of the scattered photon. Well, the wavelength of the scattered photon is just the wavelength of the incoming photon plus delta lambda, or 0.0034 plus 0.0018. And you add those together, you get 0.0052 nanometers, which is the answer. Now, remember that the electron recoils and takes away some of the energy. So the scattered photon is always lower energy than the incoming photon. And therefore, the scattered photon is always a longer wavelength. So if you can't remember whether this is a plus or a minus here, just remember you have to have the scattered photon have a longer wavelength than the incoming photon. Problem 2. Okay, you have an electron in hydrogen. So this is the Bohr model. Drops from a large value of n to n equals 1. So it's up here near n equals infinity, and then drops down to n equals 1. This is the most energetic photon that hydrogen can release. What is the wavelength of the released photon? Well, we can just use this Balmer formula. Actually, this would be the Rydberg formula, because Balmer formula is just for when it goes to the second level. But 1 over lambda is equal to Rydberg constant 1 over 1 squared minus 1 over infinity squared. Well, 1 over infinity is 0, and 1 over 1 squared is just 1. So you get 1 over lambda is equal to Rydberg constant. Or, taking reciprocals, lambda is equal to 1 over the Rydberg constant, which gives you 91 times 10 to the minus 9 meters, or in other words, 91 nanometers. Again, that is the most energetic, or the shortest wavelength photon that you can get out of the hydrogen model. Problem 3. The Broglie wavelength for an electron traveling a tenth of the speed of light. Tenth of the speed of light, you're still pretty safe using non-relativistic mechanics, and that's what we'll do. So you have the Broglie wavelength is equal to Planck's constant over the momentum, or mv. So Planck's constant, the mass of the electron, and its speed is 1/10 times the speed of light, 3 times 10 to the 8th. Do the calculation, you get 2.4 times 10 to the minus 11 meters, and you convert that to nanometers, you get 0.024 nanometers. Problem 4 is just one of these history questions. What scientist isolated radium and polonium? That would be Marie Curie. More properly, it was Marie Curie and her husband. They started with tons of uranium-containing rocks, and they ended up with just a tiny little speck of radium, and then eventually polonium that they were able to get. And it was highly radioactive when they got down to pure radium. Question number 5. Okay, thallium-206 decays by beta decay to what? Now remember, I can't use subscripts and superscripts in WebAssign, so I will say thallium-206. But you should realize, and you should use the appendix in your textbook to find that thallium is Z is equal to 81, atomic number 81. So you may have to search through that appendix to find where thallium is. It's atomic number 81. So this is 81 and 206. It goes to an electron, and with our bookkeeping procedures, we represent an electron as a -1 subscript and 0 superscript. And now you have to balance on both sides. So if you have 81 here and you have a -1 here, you got to have element 82. And 206 here, 0, you got to have 206. So element 2 with 206 mass number is Pb, or lead 206. So the answer is lead 206. All right, number 6. The spectrum, this would be the black body spectrum, is shown here. Intensity versus wavelength. What is the temperature of this object? Okay, well, this is a case where you have to get some data from the plot. Remember, what you're looking for is we need to get the maximum of the temperature, so we use Wien's displacement law. So you look carefully at that plot, and it's a little clearer on the figure in the exam, but the peak is around 500 nanometers. So from the plot, we're going to say lambda is max is 500 nanometers. Then we're going to use Wien displacement law, and we're going to divide through by lambda max. So we get this constant 0.0029, which was in the Wien displacement law, divided by your wavelength, 500 times 10 to the 9th. You need to convert it to meters. And the temperature comes out to be 5,800 Kelvin. So it's an absolute temperature. So you can calculate then, this would probably be some star with a temperature of 5,800 degrees Kelvin. So you want to be comfortable getting data from a figure as well as just plugging data into equations. Here's another history question, but this one is asked what scientist fired alpha particle at gold foil and discovered from the scattering that the atom has a heavy nucleus at its center, and that is Ernest Rutherford. Okay, this one hadn't really talked about mirror nuclei, but mirror nuclei is defined in the problem as having the neutron number and the proton number or atomic number interchanged. So one of these is not a mirror nuclei. Well, we have to go through all of them and check. This is carbon 13. Carbon 13, well, carbon is element 6. You can look it up in your appendix. So it has 6 protons and therefore 7 neutrons. Nitrogen is element 7. So 7, 13, that means it has 7 protons and only 6 neutrons. That's a mirror nucleus. And you can go through, but you find that potassium 40, potassium is element 19, and since they add up to 40, that means it has 21 neutrons, 19 protons, 21 neutrons. Calcium is element 20. Calcium 40 has 20 protons and 20 neutrons. These are not interchanged. No, this is not the case. All the rest of them do work out. I won't go through all of them, but look at hydrogen 3, that's tritium sometimes called. It's 1 proton and therefore 2 neutrons. Helium 3, which is another type of helium, has 2 protons. It's helium, and that means only 1 neutron. It's a mirror nucleus. So it's the potassium, calcium, so the answer is potassium 40 and calcium 40 are not mirror nuclei. Even though they have the same mass number, they don't have their number for neutrons and protons just interchanged. Okay, potassium 40 captures an electron to become what? Well, we talked a little bit about electron capture. All you really have to do is you take potassium 40. Let's look up what the symbol is in this notation. Well, potassium is K, and it has an atomic number of 19. You can look those up in your appendix. So you have potassium 40 plus you capture electron. That means you take your -10 electron over here on this side of the equation. And now you have to balance with a nucleus on this side. So you get 19 minus 1, so that's going to be element 18. 40 plus 0, so it's going to be element 18 is argon. And so this is argon 40 or argon 40. All right, so well, this is a case where I give you a bunch of equivalent versions of the Rydberg equation. And the Rydberg equation in the book is 1 over lambda is equal to the Rydberg constant times 1 over m squared minus 1 over n squared. Now, if you want to solve this for the wavelength, because all the solutions had the wavelength equals, you just take a reciprocal of both sides. So you now have lambda equals, you have 1 over the Rydberg constant. Here you have 1 over m squared minus 1 over n squared. Now the next step is to multiply top and bottom by m squared n squared. So there you get your m squared n squared here. On the bottom, when you multiply by m squared n squared, the m squared will cancel this m squared, and you'll just get n squared. And in this case, the n squared will cancel that n squared, and you get minus m squared, and you get n squared minus m squared. So this is equivalent to the Rydberg equation. All those other examples that were in the problems are not equivalent to the Rydberg equation. They are just other answers that I made up. Okay, so also remember, all these answers were written as basically pictures of equations, and it's a little bit hard to tell where the little bullet that you click on goes with which picture. So just be really careful to make sure you get the right bullet for the right picture. Halfway through. The photoelectric experiment, what is the slope? So it's looking for the slope of this line right here. Well, if you remember the photoelectric experiment, the kinetic energies of the electrons released is equal to the energy of the photon that comes in, hf, minus the work function. That's just conservation of energy. And if you plot kinetic energy versus F, the slope's just going to be h. That's that factor right here. So you're looking for a slope that's equal to Planck's constant. Now, if I had written the slope in joules per hertz, which is equivalent to joules times seconds, you would just write down Planck's constant. But I had given it some funny units, so you got to do the unit conversions. You're always going to have to be very comfortable converting from electron volts to joules, or joules to electron volts. And terahertz, well, I think I gave that in the problem. A terahertz is a 10 to the 12th hertz, so that's another unit conversion. And when you do all the conversions, you get 0.0041 electron volts per terahertz. Just another way of writing Planck's constant. Okay, here's a problem where you have charcoal. When you analyze that charcoal and you find the ratio of carbon-14 to carbon-12 is 0.21 parts per trillion, or 10 to the minus 12. But and then currently in the atmosphere, which we assume has been constant for a long time, the ratio of carbon-14 to carbon-12 is 1.3 parts per trillion. So what do you assume that once the plant that gave rise to the charcoal died, right when it died, it had 1.3 parts per trillion, and then it started decaying. And you want to know how old is the charcoal? So this is a classic example of carbon-14 dating. Well, you know that the half-life of carbon-14 is 5,730 years. That's given in the problem. It's also in the book. So you can immediately calculate the decay constant, which is 0.693, that's log of 2, divided by 5,730, the half-life, and that gives you a decay constant of 0.00012 inverse year. Notice you don't have to convert everything to seconds, which would be really a pain if you had something as long as thousands of years for a half-life to convert it to seconds. But if you use seconds in both the decay constant, you use years in the decay constant and the time, everything works out. So 0.21 parts per trillion equals 1.3 parts per trillion times e to the minus decay constant times time, and the time is what you're looking for. Well, it doesn't really matter whether these units are parts per trillion, 10 to the minus 12, or anything else, as long as they're the same units. When you go and divide by the 1.3, the parts per trillion always cancels. This is a dimensionless number. It's just a ratio. So I didn't really even have to specify what the units were, parts per trillion, as long as these both numbers have the same units. You're good. So you get 0.21 over 1.3 is equal to e to the minus 0.00012 times time. Now, you take the natural log of both sides. When you take the natural log of this side, it gets rid of the exponential because they're inverse functions of each other. The natural log of this side is going to be the log of 0.21 over 1.3. And again, make sure you know on your calculator how to do natural logs. And you're just left with what was in the exponent, minus 0.00012t. This number is less than 1, and the natural log of any number less than 1 is itself negative, so the negative signs cancel out. This comes out to be 1.823, and then you divide through by this decay constant, and you get a time that is 15,200 years. So it's basically 15 millennia. You can tell how old that charcoal is. Classic carbon-14 dating problem. You can be highly likely you'd see something like that on the exam. Problem 13. Hydrogen 2 and oxygen collides into oxygen 16. So you're taking deuterium and you're ramming it into oxygen 16, the most common isotope of oxygen. And what comes out is fluorine 17 plus what? Well, I think the easiest way to do it is to convert this into our usual notation. Hydrogen is element 1, and if it's hydrogen 2, you have a superscript, plus oxygen, which is element 8, superscript 16, and you could put those together, and you have to have 1 plus 8 is 9 on the bottom, and you have to have 18 on the top. Well, here the fluorine already is element 9, has a 9 on the bottom, and 16 plus 17, 18. It needs 18, and you have 17 here. So what you need is nothing on the bottom, and you need a 1 on the top in order to balance things. 0, 1, that is a neutron. So the answer is this is a way to produce neutrons. Now we have a Henry-Moseley problem, and as promised, I gave you the equation that Moseley uses for the energy of the K-alpha photon in terms of the atomic number. And it asks, what is the wavelength of the K-alpha line for lead? Well, first thing you need is the atomic number of lead. So you look it up in your appendix. Atomic number for lead is 82. So you get 82 minus 1, that's 81. And you square it times 13.6, and that gives you 89,230 electron volts, and you convert that to joules. You need to be able to do those conversions and do them quickly. 1.43 times 10 to the minus 14 joules. Well, you know the energy of a photon is hc over lambda, so you can solve that for lambda. It's hc over E. There's Planck's constant, speed of light. There's the energy you just found in joules. Don't forget to do the conversion to joules or you'll get the completely wrong answer. You get 1.38 times 10 to the minus 11 meters, which is, rounding off to two significant figures, 0.014 nanometers. You know, sometimes when you round off things, you can get slightly different answers than are in the choices on the exam, but usually I separate the choices on the exam. There's none that are real close together. So as long as you use a reasonable number of significant figures, you should be in no problem with getting the with running into two answers that look like they might both be correct. They should be well separated and you should be able to figure it out. Problem 15, fission. The example we gave in class of fission, where one of the products was barium, is just one example of the many ways fission can work. And the question is, what happens if you take a neutron, you fire it uranium-235, and it undergoes fission, and you get zirconium-99 plus 3 neutrons plus something else? What is the something else? Well, again, I find it easiest to write it out in this notation. A neutron, 0,1, plus uranium, element 92, 235, goes to, and I looked up zirconium in my appendix, it was element 40, 99, plus 3 neutrons. Now things have to balance. You got 236 on the top here, you got 99, 100, 102 here, so that leaves to 134 for the mass number of the thing we're looking for. And you have 92 on this side for protons. Here you have 40, so that leaves 52. So you know it has 52 protons and 134 neutrons plus protons. You look up in your appendix, Element 52 is Te, or tellurium-134. So that's not, again, there are many things, dozens of ways uranium-235 can break up, and that's why you get such a mess of radioactive waste products, all sorts of radioactive waste products, when you undergo fission in a fission reactor. Problem 16. This is the Rutherford scattering formula, and I promised I'd give you the Rutherford scattering formula. And the problem asks for the ratio of the number scattered at 120 degrees versus the number scattered at 60 degrees. So you're going to take a ratio, n over 100, theta equals 120 over n for theta equals 60. And all this other stuff that doesn't depend on theta will all cancel out, because you're saying everything else is equal, they're just different angles. So the only thing that survives is a sine to the fourth of theta over 2. But it's in the denominator, so if you want n of 120, that's going to be downstairs, sine to the fourth of 120 over 2. And n of 60 is going to have it upstairs, sine to the fourth of 60 over 2. And so that's going to be sine of 30 over sine of 60. And you can raise each to the fourth, but I kind of like to raise the whole ratio to the fourth. You know, a to the fourth over b to the fourth is a over b quantity to the fourth. So sine of 30 over sine of 60 is just 0.577. You raise that to the fourth, and you basically get 1/9, or 0.11. And that's the ratio you're looking for. Okay, here's a history question. What experiment did Rutherford not do? Well, he did so many that it's easy to write an equation like this, because I have 5 there experiments that he had studied, and the one that he did not do is he did not bombard uranium with neutrons. Fermi did that, and then the folks, Lisa Meitner and her collaborators Otto Hahn and Strassman did that. Rutherford didn't. If Rutherford had survived another year or two, he may well have started bombarding uranium with neutrons, but he didn't do that himself. Somewhat of another history question. The Manhattan Project. Well, we talked about the entire book, Making an Atomic Bomb, which is really focuses on the Manhattan Project. And in the Manhattan Project, you had to really separate 2 isotopes. The 2 main isotopes that needed separation were uranium-235, the one that undergoes fission, and uranium-238, which is the most common isotope of uranium. So, in some ways, the Manhattan Project was all about separating those 2 isotopes. Okay, here is an uncertainty principle problem. You have the speed of a particle, of an electron, is 0.07 plus or minus 0.03 times the speed of light. What's the uncertainty in its position? So you have delta x times delta p. Delta p, the uncertainty in the momentum, is just mass times delta v, is equal to Planck's constant over 4 pi. I should say greater than or equal to, but the problem says something about having the best possible instruments, so we're going to take it at the smallest value. We're going to take it replace the greater than or equal to by equal to. Solve it for delta x, you get h over 4 pi m delta v. So 6.6 times 10 to the minus 34, that's h, 4 pi, the mass of the electron, because it was said this was an electron. And you don't really care about the 0.07. What you care about is the uncertainty, and the uncertainty would be the plus or minus value. So 0.03 times the speed of light is the uncertainty in the speed. You never need to use the 0.07. And you do the calculation, you get 6.4 times 10 to the minus 12 meters, and convert that to nanometers, it's 0.0064 nanometers. Heisenberg uncertainty principle. And the last question. Photoelectric effect. Okay, so this is a problem where it says the photoelectric effect, you shine light onto a metal, this is the wavelength, 454 nanometers, and you use an intensity of 3 watts per meter squared. And what you get off is electrons coming off with an energy, kinetic energy of 4 electron volts. Suppose you take the same wavelength light and you increase the intensity to 6 watts per meter squared. What is the kinetic energy now? This is a little bit of a trick question, because in the photoelectric effect experiment, the kinetic energy of the electrons does not depend on the intensity. So it's the same as it was before. You got 4 electron volts with an intensity of 3, you're going to get 4 electron volts with an intensity of 6. You'll get twice as many electrons, but each electron will have the same kinetic energy, 4 electron volts. So folks, that is practice exam 2B. So all that's left to do now is to take the exam on Monday, and I wish you all the best luck. I just want you to know it's been a pleasure teaching you. I know this has been a challenging semester, but I wish you all well, and both on the exam and in your future studies.